Hello, hello, it is Mrs. Edwards and we are back. It is time to do math and I love it. Today we're going to be solving some exponential equations and we're going to be using what's called the one-to-one property. This is really considered a shortcut when solving equations that have variable exponents. Normally we don't start with a shortcut. So I want to just preface this with, in general, when you see a variable exponent, the first thing that should come to mind is logarithms. Okay, but in this case, we are going to essentially force the base numbers to be equal. And once the base numbers are equal, then we can just set the exponents equal to one another. So that one-to-one property here is if a to the m equals a to the n. Notice the bases are both a, then the exponents are equal to one another. I also put here, just for your convenience, a reminder of your exponent rules that you'll be using to force the bases to be the same. When you have like bases and you're multiplying, you add exponents. When you have like bases and you're dividing, you subtract the exponents. Any number to the 0 power is 1. If you have a number to a negative exponent, you can rewrite that as 1 over a to the n in that case. And then another just really nice property is if there is a negative exponent on an entire fraction, you can just take the reciprocal of the entire fraction and change the negative exponent to a positive one. Before we solve some of these exponential equations, I want to point out some of the common mistakes. Quickly there, if we have a 2 in front of a plus b to the third power, you cannot distribute a number through because we want exponents to come before multiplication. Okay, so never distribute a number through a set of parentheses when there's an exponent on it. The other one is there's no such thing as distributing an exponent over addition. You would need, if this was a plus b to the second power, you would take a plus b times a plus b FOIL and you end up with a middle term. So please remember when there's addition or subtraction inside of the grouping symbols there is no such thing as distributing an exponent. Let's go ahead and get started solving some of these exponential equations using that one-to-one property. Using the one-to-one property, we want to force the bases to be the same. So you're on the lookout for, perfect squares, perfect cubes, and so forth. The base on the right-hand side is 2. So thinking about that, how could we rewrite 16 with a base of 2? Well, 2 times 2 times 2 times 2 is 16. So I've rewritten 16 as 2 to the 4th. We now see we have like bases that are both 2. Using the one-to-one property, we can set the exponents equal, continue solving, so subtract 2, and we end up getting the answer x equals 2. If you did not make any algebra errors while solving, you don't have to check your solutions because you only have to check your solutions when the original equation has an x in the denominator, an x underneath an even root, or you're taking the logarithm of x. In each of those scenarios, domain issues could happen, which would lead to extraneous solutions. So I'm not going to check because I'm going to trust the algebra that I just did. But no, if you want to, you sure could. Okay, let's take a look at several more examples. Rewriting with the same base. I could write 9 as 3 to the second power. Now those bases 3 are matching. Set the exponents equal, continue solving, and I get 1. In this example, looking at 1/3 and 81, trying to think of perfect squares, perfect cubes, and so forth. 81, you might be thinking of 9 squared, but I'm not going to be able to rewrite 1/3 with the number 9. So continue to think, and each of those 9s is made out of 3 times 3. So I am going to rewrite the fraction 1/3 as 3 to the negative 1. Rewrite 81 as 3 to the 4th power. We're starting to see those matching bases emerge. Power to a power, multiply. So negative 1 times x is negative x. There we have those matching bases. So we can set the exponents equal, divide both sides by negative 1, and x equals negative 4. In this example, to force the bases to be the same, we're going to need to be able to rewrite root form as exponential form. So the cube root of a to the 4th is a to the power of, and then that fraction gets created the inside exponent over the outside index number. So it's a to the power of 4 over 3. I think of it as inside over out, like you turn a shirt inside out. And then there on the right side, I'm going to write 1 over a as a to the negative 1. Okay, so went from root form to exponential form. Over here on the right, we have a power raised to a power. The rule there is power to a power. Multiply, all right, we want to multiply negative 1 times x plus 5. So negative 1 times x is negative x. Negative 1 times 5 is negative 5. Now we can see that the bases match, allowing us to simply set the exponents equal. Continuing to solve to get x by itself, I will add 5 to both sides. I need a common denominator. 5 is the same as 15 over 3. Combine, we get 19 over 3. Continue to get x by itself by multiplying or dividing both sides by a negative 1. And x equals negative 19 over 3. Here we have another one. We could force the bases to both be 4. We could even go with base 2. It really doesn't matter. I like to go with whatever the larger base is that I have a choice between. Again, I could rewrite 4 as 2 squared and 16 as 2 to the 4th, but I'm going to go with 4. Leaving the left side exactly as it is, rewriting 16 as 4 squared, starting to see those bases come together. On the right side, power to a power, multiply. 2 multiplied by negative r is negative 2r. There we have matching bases, so I'm going to set the exponents equal. Little algebra reminder, I start to move the variables to the same side by adding 2r. If you add 2r to both sides, we end up getting negative 3 equals 0. There's a couple of things that just happened. Number 1, all of the variables dropped out. Whenever that happens, your final answer is either going to be no solution or all real numbers work. The difference is if all the variables drop out and you end up with a false statement like we have here, the answer is no solution. We are going to force those bases to be the same. I'm going to go with 5 as my base this time. 5 squared is 25, and 5 to the 4th is 625. You could have gone with base 25 and rewritten 625 as 5 squared. You'll end up with the same answer in the end. Just want those bases to be the same. On both sides, power to a power. Multiply. So 2 multiplied by 2n is 4n, and 4 times n is 4n. Some of you would notice right away, without even using or applying our one-to-one property, that both sides are equal. So no matter what number I plug in for n, these two things will be equal to each other. I'm going to go ahead and follow process. So I've made those bases the same, 5 and 5, set the exponents equal. Now, I'm not dividing both sides by n. Okay, I'm going to move numbers to one side, letters to the other. So subtracting 4n from both sides, I have 0 equals 0. All the variables dropped out, but this time we are left with a true statement. Therefore, all real numbers. No matter what number I pick off the number line, I can substitute it back into the original and it will make a true statement. Okay, so there 4n equals 4n plus 0. Subtract over 4n, 0 equals 0. I'm going to do 3 more examples. It might be overkill for examples, but I'm trying to make sure that you are seeing every scenario out there. Going to force those bases to match up. Notice that we are multiplying two things together that have like bases. So when you have like bases, you add exponents. Adding those exponents, I'm going to have negative 2v plus negative 2v, which is 0. Those bases are now matching, right? We have 1 power equals 1 power, not multiple powers. Don't just start dropping those 4's off like crazy. Okay, 1 power to 1 power, set the exponents equal. 0 equals negative v. Divide both sides by negative 1 and v equals 0. Here we have a lot going on. I would recommend getting your power alone. Notice we have a to the n equals a to the m. I want to get this 1/3 x to the 5th by itself before I try to start forcing bases to be the same. To do that, I'm going to divide both sides by 36. Dividing both sides by 36, I have 4 over 36. Might as well simplify that fraction. 4 fits into 4 once, and 4 fits into 36 9 times. Now looking at those bases currently, 1/3 and 1/9, what kind of numbers, perfect squares that you're thinking of? Hopefully you're thinking 9 is 3 squared. I'm going to rewrite 1/3 as 3 to the power of negative 1, the 9 as 3 to the 2nd. I'm going to be able to change the 1 over 3 squared to be 3 to the negative 2. On that left-hand side, we had a power to a power. Multiply. So negative 1 times x over 5 is negative x over 5. Now we have those matching bases. Set the exponents equal. To finish solving, multiply both sides by negative 5. And our final answer is 10. There are so many ways to get these bases to match. So don't think just because you go another route that you are doing it incorrectly. You know, another person right here at this step, 1/3 to the power of x over 5 equals 1/9. Maybe you rewrite 1/9 as 1/3 to the 2nd power. You quickly get those matching bases. And if we had 1/3 to the 2nd power, I could set the exponent x over 5 equals 2, and we'll end up getting to 10 a lot quicker. Last example, but maybe with a couple variations. So here I have fractions within fractions. My first instinct is always to multiply both sides by the denominator. So that's what I'm going to do, is multiply both sides by that, giving me this here. Now I'm going to work on getting those bases to be the same. 1 over 8, 1 over 16. 8 is 2 times 2 times 2, and 16 is 2 times 2 times 2 times 2. So I'm going to rewrite 8 is 2 to the 3rd, and 16 is 2 to the 4th. I'm going to cross that fraction bar line to change the sign on the exponent. So 1 over 2 to the 3rd is going to become 2 to the negative 3. And 1 over 2 to the 4th is going to become 2 to the negative 4. Here we have power to a power, multiply. So I'm going to multiply negative 3 times negative x minus 3 and negative 4 times negative 2x minus 3. Now we have those matching bases, setting the exponents equal. X is on one side, numbers on the other. I subtracted 8x from both sides and 9 from both sides. Divide both sides by negative 5, and there we have our solution. There are so many ways to tackle this problem. I started off by multiplying both sides by the denominator because that is just what I have a tendency to do as a first step. You may, however, just start working on that left-hand side, getting a base in general. Rewriting 1 over 8 as 1 over 2 cubed and 1 over 16 as 1 over 2 to the 4th. Then changing the 1 over 2 to the 3rd to 2 to the negative 3 and 1 over 2 to the 4th to 2 to the negative 4. We see power to a power. Multiplying negative 3 times negative x minus 3 and negative 4 times negative 2x minus 3. We would have that. It may occur to you right here to multiply both sides by 2 to the power of 8x plus 12, and then we would have like bases. If that doesn't occur to you, we see like bases, subtract exponents. And then subtracting, so distribute that negative through, negative 8x minus 12 and combine. We now are kind of stuck with this 2 to a power, and the right-hand side we don't have as 2 to something. It's nice to file away, though, if you are using the one-to-one property, that anytime you have the number 1, you can rewrite it with any base you want, because any base to the 0 power equals 1, forcing there to be like bases there on both sides, matching bases. Now I could set those exponents equal. There are so many ways for you to force those bases to match, and it's all right if you do it differently than someone else. As long as you have applied those exponential properties correctly, you will end up with the same answer. But I like this last problem in particular because it gives you maybe some strategy ideas that when you see a denominator, multiply both sides by the denominator, or if you see the number 1, to know that you can force the number 1 to be any base you want. If I wanted it to be base 4, I'd make it 4 to the 0. Here I wanted it to be base 2, so 2 to the 0.